So the black body is the ideal emitter and absorber, and real surfaces don't emit or absorb radiation like the black body. And so if you think about what a black body might do with respect to temperature in terms of its emissive power, we know what that looks like using the Planck distribution. So black body has this Planck distribution defined E lambda B. And what a real body might do is it might have some peaks and valleys and jagged regions that look like this. So this is E lambda B, and this is E lambda for a real body. The ratio of these is called the emissivity. And in this case, what we have is the spectral emissivity because it's wavelength dependent. So the comparison is that we have to understand how this emissivity behaves, and in fact, there is a spectral directional emissivity, so there's an emissivity that is directionally dependent. So it's both wavelength dependent and directionally varying. So you might define it as the intensity in a particular direction and a wavelength interval for at some temperature compared to the black body. And notice here that the black body, we don't have theta and phi because we know that the black body is a diffuse emitter, so it emits in all directions equally as far as the intensity. It has the same intensity in all directions. And the reason that that can be true is because the intensity is per projected area. It's a heat transfer rate per projected area. So for a black body, I lambda B is not a function of theta and phi. If we're talking about the total directional emissivity, it means that we're looking at the directional emissivity, no wavelength dependence, divided by the black body total emissivity, again, no wavelength dependence. One of the things that you want to notice then is that as we look at the hemispherical spectral emissivity, so hemispherical meaning that it's over the hemisphere, spectral meaning that it's wavelength dependent, that it depends on the directional spectral intensity integrated over the hemisphere divided by the same black body quantity integrated over the hemisphere. Why that's interesting and relevant is that we can use the spectral directional emissivity to create this definition. The way we're doing that is that earlier in the above we had I lambda, so directional in the numerator here, I'm going to call I lambda the same as this I lambda E lambda theta phi t. So if I had that quantity which was in the numerator, this quantity is equivalent to epsilon lambda times I lambda B. So if I have I lambda B in the numerator and the denominator, you see this I lambda B in the denominator here, I'm replacing this I lambda E by epsilon directional times I lambda B. I know that I lambda B is not a function of direction, so I can pull it out of the whole definition, and I cross it out, I divide it equally out, and I just get this result. The denominator is easily integrated, so I can integrate the denominator because it's just our standard integration for this hemisphere modified with this cosine theta. And what we see is that E lambda, or epsilon lambda then, can be defined really just in terms of E lambda over E lambda B, just as equivalent as we could define it above here in terms of the directional quantity. So in this case, we define it in terms of the directional value. And if we know the directional value, by directional value I mean epsilon lambda prime, then I have epsilon lambda. I get the total value from the spectral directional value. Here what we're saying is that we can get the spectral value in terms of the spectral emissive power divided by the blackbody spectral emissive power. And in this case, what we're doing is we're using the same idea where we can relate E lambda to epsilon lambda prime E lambda B prime over the hemisphere. So the same idea that we used before is that we can always relate to a lower emissivity. We can always relate to an emissivity that sort of corresponds to the unintegrated value, whatever the integrated value that we're interested in is. Sort of like the engineering quantity that we sometimes use is just the total hemispherical emissivity. And using the same arguments, that is defined in terms of the blackbody emissive power divided, the emissive power divided by the blackbody emissive power, which can be discussed in terms of the integration of epsilon lambda E B lambda d lambda over EB. And this actually goes towards this idea of a band fraction, if you recall, because what we're doing here is epsilon lambda EB lambda, which is the Planck distribution, and I'm just going to sort of make it a little bit clearer here, divided by sigma t to the fourth. Remember, and then we did a t here times t here. So this looks a lot like what we did in terms of the band fractions. What it's saying in an interesting way is that if we know epsilon lambda's functional form, then as we integrate it with respect to the band fraction, we can find out what epsilon is for that problem. And for simple representations of epsilon lambda, for example, if it's piecewise constant, then we get very simple relationships there. In terms of reflection properties, we've talked really about one type of problem so far, and that's a diffuse problem. The diffuse problem is where there is no directional variation in the properties. For reflection, we can have two types of reflections. We can have specular, which is a mirror-like reflection, or diffuse, which for many engineering surfaces is a good approximation, is this non-directional reflection. You can think about this again for problems of interest. We have some sort of incident radiation. We're going to call the incident radiation G. And another way of saying that is it's the irradiation. And several things can happen to that incident radiation or irradiation. The irradiation can be absorbed, it can be transmitted, or it can be reflected. In terms of the reflected property, the reflectivity is given the symbol rho. And rho defines the fraction of the incident reflection, of the incident radiation that's reflected. Rho itself can be a function of lambda. So we can have rho lambda, and actually it has an interesting property called bidirectionality, meaning that it depends on, for example, the possibility of the incident and the reflected directions. So rho's a relatively complicated parameter. For our purposes, again, we consider the incident radiation. We're going to have a much more simplified case. We call the incident radiation or the irradiation G. And so this G lambda, which is the spectral irradiation, is dependent on the I lambda incident cosine theta. Said differently, G is defined in terms of actual area. So it's the heat transfer rate per unit actual area in some solid angle interval per some wavelength interval. So as we look from surface dA1 out, we ask the question, if we look in some d omega window in theta phi, so this is our representation of the direction, and we have some incident radiation I lambda I coming in, then G is just that total heat transfer rate per my real area, again, d omega d lambda. Remember that I lambda I is always in terms of the projected area. So the difference between I lambda I and G is the projected area versus the true area. The hemispherical spectral irradiation just means that we're integrating over the hemisphere. So this is the spectral hemispherical. Radiation. And so it's the rate at which the radiation from all directions at wavelength lambda is incident on the surface. And the total irradiation, not surprisingly, is just the integration over all wavelengths. So it's all directions, all wavelengths. We might say it's the hemispherical total, just to be clear. Okay. If the incident radiation is diffuse, the same argument that we used for the emissive power is applicable for the irradiation. And what that says is that the spectral hemispherical irradiation is equal to pi times the incident directional intensity. Okay, so let's make sure we understand that. It says that this statement is a statement that I lambda I is not directionally dependent and that G lambda, which is the hemispherical spectral irradiation, is equal to just pi times this directional valued intensity. And a lot of times this is just going to be really, we're going to be dealing with this as in terms of a black body, so it's really I lambda B that we're going to be identifying that with. This statement is just that the total hemispherical quantity can simply be related to the total directional I value also. Total hemispherical irradiation is equal to pi times IB, where IB is this total value for the integration of I lambda I over all wavelengths. This sets up our discussion about what it means to talk about the power output from a surface. So from a surface, we know that we have G, which is the irradiation coming in. The object, the surface itself, is at some temperature, and so there's emission from that surface. The emission from that surface is E epsilon times EB, so that it's E value. And there's some reflected radiation, which is rho G. So when we think about that, the sum of the stuff that comes off of the surface is called the radiosity. So all the radiation coming off of the surface is embodied in this parameter called the radiosity. And we are using the notation J to describe the radiosity. So said differently, J is equal to epsilon EB plus rho G. It's the stuff that's emitted from the surface. It's the emissive power of the surface plus what's reflected off from the surface. There is a spectral radiosity, which is defined in terms, we rarely use this definition, so I don't really even need you to think about this too much, but it's just note that similar to what we've done before, if we know the emitted intensity and the reflected intensity, and these are diffuse, then the radiosity itself has a similar form as what we got for the irradiation and the emissive power. Like I said, this is unlikely to be something that we're going to spend much time with. What's much more important is an awareness of the energy conservation on the surface. So the energy conservation principle from the surface sets up something called Kirchoff's law, or some ideas about it. And what it basically says is just that the incident radiation is equal to, so you can formulate this from an incident perspective. It says the incident radiation is equal to reflected radiation plus the absorbed radiation and plus the transmitted radiation. So said differently, the incident radiation, there are only certain things that can happen to it. It can be reflected, it can be absorbed, or it can be transmitted. If we divide by the irradiation, the parameters that we get are the reflected portion over the incident portion, which is considered the reflectivity, the absorbed portion divided by the incident portion, which is called the absorptivity, and the transmitted portion divided by the incident portion, which is called the transmissivity. And here it's specified in terms of spectral quantities, but we can also think about this in terms of total quantities, which has to be true globally from an energy conservation idea. So for the total quantities, this is true. If we had an opaque material, remember an opaque material is a material where there is no transmitted radiation, in which case the only two pieces that we would have are the reflected piece, opaque is no transmission, so we'd have reflection and absorption is equal to 1 in the spectral sense, and in the total sense, reflection plus absorption is equal to 1. And we need to be very careful about these statements. And so what we're going to do next is we're going to talk about so-called Kirchoff's law, that it helps us understand sort of the overall issues associated with statements about both the absorptivity, reflectivity, and the emissivity. So that it helps us understand these relationships.